In this video, I will focus on Sankey diagrams. Sankey diagrams are visual representations of the flow of the energy in a device or in a process. They are always drawn from left to right. Sankey diagrams are a type of flow diagram in which the width of the arrows is proportional to the flow rate. Let's say the total energy in for an electric lamp is 100 joules or 100%. This is the width of the total energy in. Here I have the useful energy, usable energy. The width of the arrow is this, proportional to 75 joules, smaller than 100 but larger than this degraded energy, the lost energy, 25 joules. You see the width of the arrow is smaller. This is why we say they are drawn to scale. So the general rule for drawing Sankey diagrams are like this. Each energy source and loss in the process is represented by an arrow. The diagram is drawn to a scale with the width of an arrow being proportional to the amount of energy it represents. The energy flow is drawn from left to right, as I mentioned. When energy is lost from the system, it moves to the top or the bottom of the diagram. Basically, the useful energy is always drawn to the right, but degraded energy up or down. Power transfers as well as energy flows can be represented. It's also drawn for power. It's the same. So it can also show the power flow. Degraded energy. I mentioned degraded energy or energy lost. It's important to recognize that in any process where there is an energy transformation, this energy is lost, degraded energy, and is no longer available to perform a useful job. So it's not usable anymore. This is degraded energy. And there is always a loss of energy like this in all energy transfers. As I mentioned, they are drawn upward or downward. Look at this sample. Coal energy is the primary source for this Sankey diagram. Let's say it's 100% or 100 joules of energy, or if you want, it's 100 watts. This is the blue, then the maximum width in this Sankey diagram. So we have downward arrows indicating energy loss or degraded energy in these different forms: transmission, distribution, domestic wiring, and so forth. Finally, just 1% of that, or 1 joule of the total 100 joule, is regarded as light radiation, the useful energy. Here, this 35, 33, 31 are indicating the useful energy or usable energy in this energy flow. And finally, you see this was just 1% available as the useful energy. An electric kettle of rating 2 kilowatt is switched on for 90 seconds. During this time, 20 kilojoule of energy is lost to the surroundings from the kettle. Draw a Sankey diagram for this energy transfer. Okay, here we must have a total energy in, some degraded energy, and part of that as the useful energy. Let's draw it. Here I have the total energy in. This is the energy in. Power is energy divided by time. So energy is gonna be PT. Let's find it according to the formula PT. I can use the kilowatt and find the total energy in kilojoule instead of using SI units. It's okay. And then energy lost, the degraded energy is 20 kilojoule, not available anymore. So the useful energy will be subtraction of these two values, 160 kilojoules. Finally, the Sankey diagram. The maximum width is the total energy in. Here I have 160 kilojoules as useful energy to heat up the water, and 20 kilojoules to the surrounding, the degraded energy. In a petrol-powered car, 34% of the energy in the fuel is converted into kinetic energy of the car, so it's useful. I have 34% of the total energy in as useful. Heating the exhaust gases accounts for 12% of the energy lost from the fuel. So we have one source of degraded energy, 12% in exhaust. The remainder of the energy is wasted in the engine, gearbox, and the wheels. Okay, so the remaining will be 100% minus 34% minus 12%. This is the remaining. Still, it's accounted for degraded energy. Use the data to sketch a Sankey diagram for the car, assuming 1000 joules of energy is released due to burning of fuel. Okay, let's find the values. Basically, we have 1000 joules of energy in, 34% of that is 34% times 1000. So it's gonna be 340 joules. This is the useful energy, okay? Here we have a degraded energy of 12%. 12% times 1000 is going to be 120 joules. And if you subtract these two from 1000, you will get 540 joules. The remaining part, actually, this is also the degraded energy. So we have two parts as the main degraded energies, main values for degraded energy, and 340 as the useful. The Sankey diagram is gonna be like that. If I have no degraded energy, the width of this is 1000. Okay, 1000 joules. The flow of energy, of course, is to the right. Now I have a degraded energy of 120 in exhaust, and the other, I try to make it, to draw it to scale, for 540 joules wasted in moving parts, wheels, gearbox, and so forth. And the other is the useful energy. So let's combine them and make it like that. This is the Sankey diagram for this car. This video is done. Thank you for watching this video and thank you for being with me. See you.